year, mainly for physicists, but also for engineers. Okay, I think we're all ready to go, aren't we? So, there seems to be some kind of an echo there. Can you hear me okay? Oh, that's that. Yeah, let's move that just around to the right a bit. I do apologise, I've got quite a bad cold today, so I'm feeling quite woozy, so I'll make less sense than normal. I do apologise. So, I did skip over a bit because I was trying to talk about Maxwell's equations and their behaviour in dielectrics. I'm going to go back just for a moment, so you can look in the notes, this is one of the earlier sections, but I thought it would be better to talk about it now. That's weird. It's still showing there. What is it? Huh? That's weird. What? How does that happen? Is it frozen? Oh, that's weird. Let's try and turn it off. Let's turn it on again. That's really weird. I've never seen that before. How's it not live? Okay, that's weird. Okay, I apologise for this. I'm not really sure what's happening yet. That's really weird. Okay, well, people are still coming in. Try that. Okay. No, it's not displaying. What's going on here? There we go. It's coming on now. And pop that on there. Should come up. It should be right. Oh, it must have frozen or something. What? That's really weird. I don't know how to make that work. Okay. There we go, got it. Right. Didn't know I did that. Okay, so remember I talked about the Lorenzes. There are three of them. Okay? Hendrik Lorentz, relativity. Ludwig Lorentz, the gauge that we saw before, and Edward Lorentz, that we don't talk about, and he's the chaos theory person. Okay? So, we look at Hendrik Lorentz's famous Lorenz force, which tells you about the force on a charge, and you remind yourself that there's no force on a charge unless it is moving at some velocity v. But of course you can work out what the force on a charge distribution, by, on the charge distribution as a whole, by integrating over some volume, whatever the charge density is in that volume, and thinking about its velocity. But it does suggest something about the nature of the force, which is there is some relationship between the electric and magnetic fields. So a moving charge is the reason it's experiencing magnetic field is it's experiencing an effective electric field by virtue of the Lorentz transformation. Okay? So it is possible to transform electric and magnetic fields. And that's what I'll just briefly show now. Okay? So all of this is in the notes. So we start by imagining a charge that is moving with some kinetic energy. So of course in the first year you did your relativistic transformations by virtue of a velocity argument. We're doing it the other way around. So we calculate gamma first and then beta. Okay? So if we have a total energy of a charge, E total, the gamma factor is simply E total over E0, and we realise that the kinetic energy is the difference between the total energy and the rest energy, which you've seen before. From that, of course, we can calculate the velocity directly. You've seen that millions of times before. And, of course, we need to be aware of the fact that the velocity, of course, in general is a vector quantity, and we need to have a vector form for beta. Okay, now, we know that two charges which are stationary experience an electrostatic repulsion between them. Okay? If those two charges are now moving rapidly near the velocity of light, we know that the magnetic force is eventually equal and opposite to the electrostatic force. Okay? So that space charge, the force that we described between the two charges, goes to zero as the velocity of the charges goes to c. Okay? Now, we can regard that situation in another way by thinking about the charges in their own rest frame, and those charges, if they are in their own rest frame, experience the same electrostatic force as they would do if they were stationary. But from our point of view, what has happened is that force has been time dilated, so whilst the force is still there, we don't see time progressing for those two charges as they're moving rapidly, so whilst the force is still there, there is no effect from that force. Okay? So we can think about that as an equivalent electric field. Okay? Now, what that means is, if I imagine some electric and magnetic field which are present in my rest frame, I can transform it to the effective electric field which the charge experiences in its own frame. Right? So the corollary of that statement is, you also have the same formula for the magnetic field. Okay? So electric and magnetic fields in one frame can be transformed into another frame by virtue of that beta value and the gamma value. Okay, so the beta value had to be expressed as a vector quantity, and the gamma value is a scalar. Now that's a fairly complex pair of formulae. I'm not going to ask you to remember that. The important thing to look at is to look at this scaling here. Okay? So I'm going to look at, imagine I have a situation where I have a rapidly moving charge, but it's moving in a medium where there's no electric field in the rest frame, so E there is 0, and the magnetic field has some finite quantity. It might be like a Tesla, a typical value for a magnetic field. Okay? When I do the Lorenz transformation of those two fields, the E that's 0 and the B that's non-zero, I have an effective electric field. Okay? So a charge that moves through a magnetic field sees an effective electric field. And that is important. Let's consider an example. In some particle accelerators, we accelerate things called negative hydrogen ions. Okay? So this is a proton with 2 electrons attached to it. One of the interesting things about that is that those electrons are more firmly attached than if there was 1 electron. The ionization energy is a little higher. So, sorry. Yes, that's right. No, that's not correct, sorry. What I mean is that the ionization energy is lower than for the second electron than it would be for 1 electron. Okay, so you have a negative hydrogen ion that's moving through a magnetic field. So this could be like a cyclotron. I have a large beam of these particles, many of these H- ions. And as those H- ions pass through that magnetic field, and the effective distance they travel can be quite long, right? You can calculate the effective electric field they see. Okay? Now, in that situation, the magnetic field is perpendicular to the electric to the velocity of the ion, and there is a simple scaling which allows me to calculate the electric field. Okay, simply beta, gamma, C, B. Okay. So let's think of a typical set of values for that. So we go to Canada and we look at the Triumph cyclotron. Let's assume that in a bit so you can see it a bit more clearly. Right. So we imagine a kinetic energy for the ion of 500 MeV. The rest mass of the ion is about the same as that of the proton. That's about 938 MeV. And when I put those values in, you should try this. You can calculate the beta value is about 0.75, and the gamma value is a little bit more than 1, it's about 1.5. And actually for moderate kinetic energies, when the kinetic energy is near to the rest energy of the species, so here it's a proton, about a GeV or so, the beta gamma value is about 1.2. So you can see that that number is about 1. The magnetic field, well, it's about a Tesla. In Triumph, it's about half a Tesla. The very important factor is C. Okay? So once you're moving reasonably relativistic, this beta gamma factor approaches around about 1, and the C value starts to kick in, and it gives you a 10 to the 8 enhancement. So your 1 Tesla magnetic field appears to the ion to be a very, very large electric field. How large? It's something like a gigavolt per meter. Right? About 0.2 in this case, a little bit less. Right? So what does that look like from the point of view of the ion? Well, if I look at it in terms of how many volts per angstrom, okay, and if I think about the electric field and the voltage that's generated over the size of 1 atom, it's of the order of 2 volts. Now we know that 2 volts, 2 eV, is about the ionization energy of most atoms. So therefore I expect that an object which is atomic-like, this is an ion, so it's got electrons going around it, but it's atomic-like, when it's moving through a magnetic field rapidly, it will experience an electric field that can be strong enough to ionize it. Okay? So that's a phenomenon known as Lorenz stripping. Okay? So that's, I think, a nice example of the transformation of magnetic fields to electric fields. So in the case of H-, the ionization energy is about 0.7 eV. So 2 volts per angstrom, okay, is enough to start causing ionization to occur. Now it doesn't just turn on, it's a progressive effect. Okay, so as the voltage, the effective field approaches the voltage required to ionize, it starts to strip more and more, but it gives you a kind of scaling value that says you can't have kinetic energies of ions above this, say, 500 MeV in a field of about half a Tesla or so. And that's why the trimer cyclotron needs to have a lowish field of half a Tesla. It's to stop this Lorenz stripping from occurring. Okay? So the main formula you need to learn is essentially that one, okay? That transformation. So take a look at these formulae and see if you can go from these two lines to that one there. Okay? Sorry. You need to be able to go from, let's zoom out. Take a look at these two lines here and see if you can transform them for that simpler case into that formula. Okay? And make sure you can calculate those beta and gamma factors, of course. All right, now, so we had Maxwell's equation, and we were able to derive from Maxwell's equations the electric and magnetic fields, and we showed that in free space or in a dielectric, where there are no sources and there are no currents, we showed that there is a wave equation. Okay, so the wave equation we obtained. Let's show the dielectric one. This is a reminder. The wave equation we obtained was that, okay, from which we could conclude that we had a velocity. Is that focus? Yeah. We have a velocity of any waves in that medium, which was dependent upon the relative permittivity and the relative permeability. And I keep reminding that the relative permeability is very often 1. Okay. Now clearly we're going to move on and talk about plane waves now, because they're the standard way of expressing interesting behaviour from that general solution. So let's start talking about plane wave solutions. Okay. So what is a plane wave? Well, we remind ourselves that a plane wave, and remember we haven't yet coupled together E and B. Remember we had two separate solutions for E and B. But we expect similar behaviour for both because we have two parallel equations. But we're going to think about situations where the electric and magnetic fields depend only on one spatial coordinate, and on t, time. Okay? So we can write down in a very general sense, let's call the dependent coordinate z. Okay? So we say the wave is moving in z. We'll think about an electric field first. We have two possible components, x and y, and we say that they only depend on z and t. They have no x or y dependence. Okay. Like so. Now we already know that so let's draw that out. And z. Let's draw y like that. I'll draw x like this. Okay. And let's draw the y component. Okay. Okay. So at any given moment in time, which is a snapshot that I'm drawing here, I have to start with some arbitrary electric field as a function of z, and this is the y component of that. Okay. Now, in the situation where there are no charge in field, there's no charges in current, we can say del dot E equals 0. Right. And therefore we know that dEz by dz equals 0. That means Ez equals constant. It's a constant value. Right. So that's a matter of convenience. We can think about plane wave solutions where I apply some static electric field in the z direction, in this direction. But for convenience, I'm just going to say that's not interesting. So I'm just going to say let's set Ez equals 0. Okay. And of course, there's an analogy with the magnetic fields. I'm also going to say, in the same manner, Ez is also equal to 0. Okay? So I'm going to consider solutions where all of E and B are only in the x and y directions. A little bit careful about that. Okay. So because I can do that, I can simplify my wave equation to, let's say, again, we talk about the electric fields first. I can simplify my wave equation as follows. Zero. So I can separate out my two components. Like so. So I have two separate components in x and y. Okay. So far I haven't said anything at all about their time variation. So again, E, X and EY are transverse to Z. And so far I've said they have some kind of form. Now, of course, because it's a wave, and it has to satisfy that wave equation, whatever the shape of that electric field is, it has initially some arbitrary shape. I know that to be a wave, to satisfy that wave equation, the electric field, that function that appears in those two terms, has to satisfy some function f, where f is a function of z minus ct. Okay, so the disturbance, whatever shape it has, the electric field moves along at c. Otherwise it won't satisfy that equation. And there must be, of course, another one that satisfies some other function, let's call it g, okay, and it also moves at the velocity c. Okay. Now, of course, I can have it as plus or minus, can't I? Right? Because if I differentiate twice, I get two minus signs appearing, and that's allowed. Okay. So, what I'm talking about here is some disturbance, and if I have some function f, okay, if it's f of z minus ct, then I have some disturbance in the electric field, some variation in the electric field which moves forwards at c, and if it's z plus ct, then it moves backwards at c. We'll go that way. But the shape remains the same. And of course that's c, of course we remind ourselves, that is the phase velocity. Now this is where we now break it down into individual components, because of course you can see that any shape of electric field, any pattern that's moving, we can build it up in terms of frequency components. Remember we said that one of the reasons we might want to do that is because we know that some of the behaviour, for example, the permittivities and permeabilities may vary as a function of frequency, because they depend on the rate at which the electrons in the atoms can move around. Okay? So we can build up any f of z minus ct in terms of components. So each component is an electric field which has some magnitude. So now what I'm doing is I'm combining together the x and the y terms. So E0 here is some amplitude of the electric field pointing in the x direction and some amplitude of the electric field pointing in the y direction. And of course at any given instant it may go up and down. Okay, and the rate at which it goes up and down for a particular frequency component, okay, looks like that. Okay? So there's the magnitude, there's the frequency, and there must be some corresponding wave number. Okay? So obviously here, if the term is omega t minus kz, then the propagation of this particular frequency component is in the plus z direction. Okay? And it's omega t plus kz, it's in the minus z direction. Okay. That's the propagation. Now the speed here, which of course in free space is c, is given by omega over mod k. Right? Now so far what we've talked about for this simple plane wave, right, k is just a scalar value, we're going to be talking about vector values later on. So we'll say mod k, okay, and again in free space that's going to be 1 over mu naught epsilon naught. So far as k is a scalar, but it will be simply a vector. And of course all this applies to the magnetic field as well, so we can write similar solutions for plane waves. We break them down into different frequency components, and we know they look like this, exactly the same. Omega t plus or minus kz. Okay. Right. Now the interesting thing, of course, is how they're related. Let's look at the free space situation. So how are B and E related? So a bit of preamble. Now we know in free space that there's a relationship between the magnetic field and the electric field. So we'll take one of those frequency components and we substitute it into that equation. So let's do it explicitly. So the left hand side, okay, we'll imagine two components, Bx0 pointing in the x direction and Vy0 pointing in the y direction, and it's some kind of some frequency, omega. I've taken the derivative, that's where the I omega has come from. And then I can explicitly calculate curl as follows. Just write it out explicitly, just once. Okay. And the electric field, I've said, has only transverse components, so there's no Z component. And when I do the d by dz, okay, you'll see that it looks like minus ik. Okay. So the right-hand side of that equation, that's the curl E, has this x direction component, okay, and then the y component looks like that. So what does that tell me? I can equate the two x values and the two y values, and notice that the y component of the electric field is related to the x component of the magnetic field, and the x component of the electric field is related to the y component of the magnetic field. Okay. So match those terms together, and immediately we see a relationship between the strength of the magnetic field and the strength of the electric field. Remember, this is all for free space. So this is for a particular frequency component. There must be a relationship between the magnetic and electric field. So there's two plane waves, but because the two plane waves are coupled together via this equation, they must have a strength relationship with each other. And I can combine those two equations together to get like a vector equation. So this would be for any particular direction of wave. I can combine it as so. So this, of course, here we're writing this. We're saying that the wave is moving in the z direction. It has a certain strength E0, and the strength of the magnetic field is given by K over omega. All right. Now let's look at what that means. Let's calculate the dot product of E and B. Well, we can look at the two components, or we can calculate them explicitly. If we write it out explicitly, and we substitute in for the magnetic field what electric field it is, we'll see very quickly that because of that, the minus sign that appears in the curl term, those two components cancel out. Okay? And that tells us something. It tells us that the electric field is perpendicular to the magnetic field. That's one fact we can find out straight away. Another thing we can see, if we look at the strength of the electric field, E0 is equal to K over omega times E0. Just derive that above. But we know that omega over K is the speed of the wave. And this is all in a vacuum so far. So that tells us that in an electromagnetic plane wave, the magnetic field is c times smaller than the electric field. So, as an example of that, imagine I have a radio antenna. And let's pick a typical electric field which might be at some distance from the antenna. So it's going to be a few millivolts as it turns out. So the strength of the electric field, let's pick a value. Let's say it's 3 millivolts per meter. Okay? 3 millivolts per meter. That's not a million miles away from being about right. So imagine the Winter Hill transmitter's got a few hundred kilowatts coming out of it. Over here, the voltage at some distance is it's going to be a few millivolts. And one of the example sheets will go through a calculation like that, so you can calculate it explicitly. In that situation, the magnetic field is of the order of 10 to the minus 11 Tesla, okay, which is extremely, very, very, very small. So let's relate that to typical things. You can measure a voltage of several millivolts quite easily. Right? It's very, very hard to measure very, very tiny magnetic fields, okay, especially in empty space. So that's one example. Now let's look at the other end of the scale. So we've got a radio antenna, a few millivolts at some distance to it, virtually no magnetic field. Okay? So this is completely splurged out by the Earth's field or any bar magnets that happen to be nearby. At the other end of the scale, let's think of some kind of high power laser. So this could be like the Gemini laser of Rutherford Appleton Laboratory. Okay? The typical kind of values for the power is petawatts these days. So it's a pulse laser where the pulse of light is focused onto a small target. You have several petawatts, you have several joules of energy, so it's over a very short amount of time, of the order of picoseconds. And when you focus that laser spot down into a very, very small point, the electric fields you can generate can be as high as 10 to the 9 volts per meter. And of course I'm writing these down in other scale forms because I think it's quite useful to write them down that way. It's about a gigavolt per meter, and of course a gigavolt per meter divided by 3 10 to the 8 means the effective magnetic field is now really rather large. It's around 3 Tesla. Okay? So those are two ends of the scale that you might encounter in reality. All right. So we can couple together the electromagnetic fields through Maxwell's equations, and they've also given us a way of describing a plane wave solution. Now let's talk about, as well as having the direction of motion of the wave, which of course so far we've talked about being in the z direction, but we can generalize it to any direction. Let's talk about a wave moving in an arbitrary direction. So we say a plane polarized wave. Let's talk about it now moving in an arbitrary direction. So rather than just z now, let's write down what happens when it's moving in some direction which is described by some unit vector k. Okay. So we write down our electric field, which in general is determined by position vector r, which we observe the electric field at the time at which we observe it. And in general, we can take that one-dimensional case and we can write it down in general terms as follows. So we'll have the omega t term there. And now we need to multiply k dot r. Okay. So that is, k dot r is the number of waves, the total number of periods I've moved. So that gives me the kind of phase change that I've had from one location to another. Right? And just as we had before, the magnetic field, rather than z, it's now k cross e. Right? So we can write it down that way, and we can write down here, this is a unit vector that points in the direction of the propagation of the wave. We can write it down that way, or we can wrap up the k and the c values together, and we can equivalently describe the magnetic field as 1 over omega k cross e, where this k value is expressed as the direction and effectively the wavelength, which is the wave number, the wavelength of the wave. And obviously, what we did for that simpler case of just propagating in z, we simply said k equals k z hat, of course. Okay, so just to recap, what are we doing? We are trying to find a way of breaking down any arbitrary electromagnetic wave into frequency components And so far we're thinking about plane wave components, and we've calculated the relationship between the electric and magnetic field. We've discovered two things. The electric field and the magnetic field are perpendicular to each other, and we've also obtained a relationship between the magnitudes of the electric field and magnetic field in free space, right? Which is that relationship there. Okay. All right. Now, let's look a bit more about polarization. Let's actually get rid of those just for a bit more clarity. Polarization. So what we've done so far is we've talked about some magnitude of the electric field, which is now propagating in some direction k. Okay. But that magnitude is composed of two parts: the magnitude of the electric field in the x direction and the magnitude of the electric field in the y direction. Okay. So let's consider different situations. So we'll start with the general situation. General EM wave, okay, propagating in the z direction. So we'll describe our electric field. I'm going to write it down as, I'm going to write it in a slightly different way. E1 and E2. Remember, there's no z component of the electric field because it's not interesting. It might be there, but it's not part of the wave. So we're going to say that E here is the strength, such that I can write down the electric field in the x direction, Ex, as being some strength value, okay, E to the I omega t minus kz, leave that bracket off just for a second, and Ey equals E2 to the I. So we're talking about situations where I have the same frequency, okay, of in both those two components, so still a plane wave. But now I'm thinking about the relationship between the electric field in the x direction and the electric field in the y direction. I realise I can actually write down two extra numbers there, phi 1 and phi 2, which are the phases, okay, basically the phase difference between when the peaks in the electric field in the x direction occur and when the peaks in the electric field in the y direction occur. Okay. But just as before, everything, you still have this situation that the magnetic field can be defined as being perpendicular to the electric field in the direction of propagation, and it has c times less strength. Okay. Now notice when I do this cross product, the magnetic field has been rotated. Whatever was happening in the x direction, sorry, whatever was happening in the electric field, okay, the magnetic field has a magnitude. Okay, at any given instant, there's a magnetic has a strength E over c. So whatever the instantaneous electric field is doing, it's c times less than that, and it has been rotated by that cross product in Maxwell's equations through pi by 2, okay, spatially. Now you already know that the amount of polarization, the polarization of the wave, is obviously determined by how much I have of one component compared to how much I have of the other component. So it's determined by E1 over E2, how big the ratio of those two numbers are. And the phase difference between them, okay, determines the polarization properties. Okay, so the degree of polarization is determined by E1 over E2, and the type of polarization by phi 1 minus phi 2. So obviously it's what we'll do is we'll set phi 1 equals 0 because it's the difference that matters. And we'll just call phi 2 phi, just for simplicity. Okay? So really my electric field, okay, looks like E1 cos omega t, so I just drop that phi value because it's not interesting. I put E2 in, cos omega t plus phi, and 0 for the z direction. Okay, hopefully you can see the interesting cases that I'm going to come across. So the simplest case first is phi equals 0. Okay? And phi equals 0 That's linear polarization. And of course in that situation, the electric field is just E1, E2, 0, cos omega t. What does that look like? It means that that's Z, right? I have E1 in that direction, E2 in that direction. So there's a plane of polarization like that. Okay? And the electric field is oscillating like that. Okay? That's what that means. Okay, so E oscillates along a fixed plane in space. So it doesn't stick out of it. So let's draw that just carefully. So I'm now going to swap axes. I'm going to call that T, and that's X. I like to draw X sort of horizontally now in my 3D representation, and then Y is now vertical. Okay. So let's consider a special situation of E2 equals 0. That means there's no electric field in the Y direction, and that means that of course my Y is doing this. So this is at a particular point in space as a function of time. The electric field is going up and down sinusoidally because it's a single frequency. Okay. And you can see that's the plane. The plane is the x-plane. Okay. But of course more generally, when I have a non-zero component in the other plane, then if that is x and that's y, then that's the plane. Okay. That's the motion. That's this dotted line, that's that plane. So now the wave is moving into the page, and the electric field may oscillate backwards and forwards. So sometimes the electric field is pointing one way, and other times it's pointing the other way. And of course that vector there, the direction in which it points, is given by E1 and E2. So that's the easy one. Another one, put a little box around it, polarization. Another interesting one is phi equals pi minus 2. I've chosen minus pi by 2 because, as we'll see in a minute, this is known as left-hand circular polarization. See why it's left-hand as follows. So I'm going to start by saying, what if E1 and E2 are of equal magnitude? Call that E. Okay. So now, the total electric field as a function of time in a given location is given by E as an x component cos omega t, and now it has a y component plus sine omega t, and of course the z component is 0, as before. And of course I can rewrite sine omega t by remembering that sine theta is equal to cos of theta minus 90 degrees. Okay. And if I draw out what's happening, so let's draw carefully. Okay. This is at a fixed point in time, looking down. Okay. So Z is into the page. So at a fixed time I may have some value of the electric field. And now what I do, I call that E at some time. And then as time progresses, the wave goes that way. Okay, so the electric field vector goes up. Sorry, it's a fixed Z position, I should say. At a fixed Z position, at a fixed time, the electric field has some particular magnitude and direction, but because it has this form, it will start to rotate in the anti-clockwise direction, as viewed in the direction of the wave. Okay. So E has a constant magnitude. Okay. And it rotates. So no prizes for guessing. that phi equals plus pi by 2, because obviously everything's going in the opposite direction. It's right-hand circular. And of course everything's reversed. X, Y, and Z. And again, at a fixed moment in time, the electric field will have some direction. Now I'm looking at some plane, some fixed position in Z, and I'll let time progress, and that direction of the electric field will start to rotate in the clockwise direction. So this is at a given Z location, and my very time, the electric field is doing that. But clearly the wave is also moving that way, which means that at a given instant in time, if I look at different planes, different Z values, then the point of that electric field must rotate in the helix, okay, where the period of that helix is the period of the wave. Okay. All right. And of course, the more general situation is when E1 is not equal to E2. So I can write that more generally. I can say that the total electric field at any given location as a function of time is equal to E1 cos omega t and E2 cos omega t, and I add in so cos omega. Let's write that again. Electric field as a function of time is equal to E1 cos omega t, E2, and then we have cos omega t plus phi, 0 in the z direction as before. And now, instead of the electric field vector, so at a given z, left-hand circular wave, not the same way as the wave curve, that way the electric field is going anti-clockwise for left-hand polarization, it's going clockwise for right-hand polarization, but they both move in a circle, whereas in elliptical polarization, the electric vector, okay, traces an ellipse. Okay, this is in time, but at a given z, okay, in time at, let's say at given z, okay, it now traces an ellipse. So those are all the separate components I can think of. Now, real radiation, of course, a very important example, let's say we think about the photons coming from the sun on a sunny day. There may be a superposition of different polarizations. There's one more case that's interesting. So this can still be a single frequency, a single wavelength of light. There may be many photons, but now we can have another interesting situation, which is that of a randomly polarized wave. And then the electric field may change randomly in time, but may have a constant magnitude. The direction may change. So what have we done today? We've looked at moving from Maxwell's equations and describing the properties of plane waves, and the reason we've done that is to look at how they propagate, how the electric field and magnetic field are perpendicular to each other, and also the relative magnitudes, and this is all for the free space situation. And we've looked in terms of plane wave solutions because we'll see that they're the approximate forms that allow us to obtain interesting solutions when we start to look at radiation production, which we'll look at in about a lecture or two. Okay. Now we've got a couple of minutes left. Now we're going to start looking at we're going to be finishing off section 1, okay, which is, remember, this is all preamble. Okay, so we'll move on to the radiation production stuff soon, and then it'll get more interesting. Right? We have to go through this bit because we need to describe the plane wave solutions first. Okay. So, The next step, which we'll go on to on Monday in detail, but let's just sketch out the starting point of that. We're going to start talking about the motion of energy in electromagnetic waves. So we're going to start with a plane wave solution. Okay? So as well as the electric and magnetic fields being related to each other, and we already saw that an electric field and a magnetic field both contain energy within them. Remember one of the previous lectures we looked at how there was a relationship between the amount of energy that was in an electric field or electromagnetic field, and how that energy could be exchanged with, say, a set of charges, and that's done primarily by the way the electric field does work on those charges, or the charges do work on the field. Right? The electromagnetic field, if it is, say, such something like a plane wave, can carry energy from one place to another. So that's obviously going to be something to do with radiation pressure. Okay? So we'll start just for a couple of minutes. We're going for time. Yeah, we've got about 5 more minutes. Okay. So we'll just begin our journey considering that plane wave that we've just been discussing. So we're going to consider a plane EM wave. And again, it's all in a vacuum. And again, we're starting with these simpler ideas before we talk about more complex ones. Eventually we'll get on to talking about things like plasmas. So, same thing again, our same plane electromagnetic wave. It's travelling in a vacuum, it's travelling in the z direction. Okay. So let's just one more time write down the electric field, and we're going to consider a simple case. Okay. It's x polarised. So the electric field is x polarised. So therefore the magnetic field is y polarised. And again, B0 is equal to E0 over C in a vacuum, okay? By virtue of that cross product. Now one thing you immediately see, this is a plane wave. A very important thing to observe at this point is that the electric field and the magnetic field are going up and down together. Okay? Maxwell's equations, that cross product, has tied together the two phases. So as the electric field goes up, the magnetic field goes up. They're pointing perpendicular to each other, but they go up and down together. Okay? I know I've said that a few times. But it's very important to see. They have the same phase. And again, I've just chosen linear polarization. Okay. Now, up till now, we simply wrote down what the energy densities in an electric field and magnetic field are, which you've seen before. So let's write them down for this plane wave explicitly. So the electric field has, at any given point in time and position in space, it has an energy density which obviously goes as half epsilon naught, whatever the electric field is, so there must be a core squared term. Okay, so clearly, because the energy is proportional to the electric field squared, the energy density must be a positive definite value. It can't be less than 0. And the same thing must be true for the magnetic field. Okay, so rather than multiplying by epsilon 0, I have to divide by mu 0. And again, it has that cos squared omega t minus kz value. So that tells you something. It tells you that if at some particular location the electric field density is large, the magnetic field density is large at the same time. They go up and down together. Okay? That's what you can see in that equation. Now, as an exercise, I'd like you to show that UE equals UB. Okay? We saw that B0 is related to E0. A few lines, you can just confirm that UE equals U0. Okay? So that tells us something. It tells us if I have an electromagnetic plane wave, or electromagnetic wave in general, it tells me that the electric field and the magnetic field carry the same amount of energy. Okay? So the total energy U is equal to UE plus UB, but because they're the same, I can write it down just in terms of the electric field. So just to finish off, I would have said that imagine this electromagnetic plane wave. This is at a fixed time. Okay? So we take a photograph of what the energy density, the total energy density, looks like. And in that plane wave, some parts of the wave, some positions have higher energy density and some have zero. And the separation between the high energy density regions is the wavelength, obviously. Right? And you can do an equivalent picture. Obviously, it goes back and forth, of course. If I look at a particular location and I see the electromagnetic wave passing over, then this is for a linear polarized single frequency wave. Okay. Obviously, the energy density rises and falls with time, with a period that's equal to the period 1 over the frequency of the wave. Okay, that will probably do for today, and we'll just remind ourselves of that on Monday, and then we'll move on and talk about how that energy can exert pressure on things, and then we'll finish off section 1. Thanks. Of course, hello. Yeah, so what's happening here? These are both unit vectors, okay? So in our simpler case of the plane wave, Z, this is the unit vector pointing along the Z direction. So this is basically saying that the strength of the magnetic field, well, the magnetic field at any given time, okay, in any given position, is equal to 1 over c times the electric field, but the vector part tells you the direction it's pointing at. The electric field is pointing that way, and the magnetic field is pointing that way. Okay? The difference between this equation and this one is here, the wave, rather than the wave going in the z direction, it can go in that direction, and if the electric field is pointing that way, then the magnetic field is pointing that way. Okay? Well, this is the general statement of this one, yeah. But both k hat and z hat are unit magnitude quantities. Okay, so k here tells you only the direction; it does not tell you the wavelength or the wave number. Okay, but k, as it appears in these equations here, that is the wave number, so it tells you about the wavelength. Okay. Hello. Yes, that's a typo. Thank you for pointing that out.
It was just when you put at the end. Is that meant to be possible on the negative side?
I think which way around it is, but I will check. Yeah. I will double check that.
Thank you very much.
I'm pretty sure that must be the handwritten version, but I'll change. Yeah, these minus signs do appear occasionally. Yeah, it's bloody important. Yeah, I will fix that.